Water has always been one of nature's greatest forces. For thousands of years, humans have harnessed its strength, first to power mills and workshops, and today to generate clean, renewable electricity. A hydroelectric power plant is, at its core, a system that converts the movement of water into electrical energy through simple yet powerful physical principles. The concept is easy to grasp. When water is stored at a high elevation, it possesses potential energy due to gravity. When it flows downward, that energy transforms into kinetic energy, the energy of motion. The hydroelectric plant captures this motion and uses it to spin a turbine, which in turn drives a generator that produces electricity. Every hydroelectric power plant consists of several key components: a dam or reservoir that stores water at a higher level. The greater the height or head of the water, the more pressure and the more potential energy available. An intake channel or penstock, which directs the water flow toward the turbine. The turbine, where the moving water hits specially designed blades, making them spin with tremendous force. And finally, the generator, which transforms mechanical rotation into electricity through electromagnetic induction. In simple terms, the chain looks like this: water equals sign, turbine equals sign, generator equals sign, electricity. To make the process efficient, water flow must be precisely controlled. Gates and valves regulate how much water enters the turbine, balancing production with demand. When electricity demand rises, the gates open wider, allowing more water to pass and generating more power. When demand drops, the flow is reduced. If you enjoy educational science content like this, don't forget to like, subscribe, and share this video with your friends. Different types of turbines are used depending on water pressure and flow. Francis turbine, the most common versatile design for medium heads. Kaplan turbine, similar to a ship's propeller, ideal for low heads and high flow. Pelton turbine uses high-pressure jets of water hitting spoon-shaped buckets for maximum energy conversion. Each type of turbine is optimized for specific site conditions, but the core idea remains unchanged. The power of moving water becomes the power of electricity. After passing through the turbine, water is released back into the river through an outflow channel, completing a closed-loop process. No fuel is burned, no smoke is produced, and no carbon emissions are released. That's why hydroelectric plants are among the cleanest and most sustainable sources of energy on Earth. Watching massive streams of water spin steel turbines that light up entire cities is a reminder that nature and physics can work together in perfect harmony. To truly understand how moving water becomes electricity, we have to look inside the generator, the beating heart of every hydroelectric power plant. This is where mechanical energy from the spinning turbine is transformed into electrical energy through one of the most important discoveries in physics: electromagnetic induction. A generator consists of two main parts: the rotor, which rotates, and the stator, which stays fixed around it. The rotor carries strong magnets or electromagnets that create a magnetic field. As the turbine spins the rotor, this magnetic field moves around the copper coils of the stator, inducing a flow of electrons. In other words, electric current. This phenomenon was discovered in 1831 by Michael Faraday, who proved that moving a magnetic field across a conductor generates electricity. Nearly every power source on Earth, whether hydro, wind, steam, or nuclear, relies on this same principle: rotation, magnetism, electricity. In a hydroelectric plant, the turbine and generator share a common shaft. The stream of water turns the turbine blades, spinning the rotor at incredible speeds, sometimes up to 500 revolutions per minute. This rotation creates three-phase alternating current, AC, which is then sent to a transformer, where the voltage is increased for transmission over long distances. The operation of a hydroelectric plant is fully automated. Computerized control systems continuously monitor the water flow, turbine speed, and electrical demand in real time. When electricity consumption rises, the system automatically opens the water gates, increasing flow and output. When demand falls, the flow is reduced. This fast and precise control makes hydro plants essential for grid stability. They can adjust power production within seconds, compensating for fluctuations caused by solar or wind variability. A special type of hydro plant is the pumped storage power plant. These systems don't just produce electricity, they also store it. When there's a surplus of energy in the grid, for example at night or during strong winds, electric pumps push water from a lower reservoir back into an upper one. Later, when demand peaks, that same water is released downhill to spin the turbines again, generating power on demand. It's one of the smartest and most efficient forms of energy storage ever invented. The famous Long Slopes pumped storage plant in the Czech Republic is a perfect example, moving water across a 500-meter elevation difference with turbines capable of producing over 600 megawatts of power. Modern hydro plants also take environmental protection seriously. Turbine designs are becoming fish-friendly, using smooth and curved blades that allow aquatic life to pass safely through. Advanced sensors monitor water quality, pressure, vibration, and temperature to ensure efficient and sustainable operation for decades. Ultimately, the hydroelectric generator is a masterpiece of physics, a machine that transforms the simple motion of water into the electricity that powers entire nations. Hydropower is not just a legacy of the past, it's a cornerstone of the future of clean energy. The principle remains the same as it was a century ago, but today's technologies make hydroelectric powers smarter, more efficient, and more sustainable than ever before. One of the fastest growing trends is the development of micro and small hydroelectric plants. These compact systems can generate electricity even from small rivers and mountain streams, without the need for massive dams or large-scale construction. Just a few meters of waterhead are enough to power a home, a farm, or an entire village. Such systems are revolutionizing access to electricity in remote regions, offering reliable, low-cost energy to millions of people. Microturbines are the key to this transformation. They are simple, durable, and require minimal maintenance. Operating for decades with almost no downtime, they provide clean energy wherever flowing water exists. Another exciting development is the rise of floating hydro systems, small turbines placed directly in the natural flow of a river. They don't alter the environment, block fish migration, or flood valleys. Instead, they harness the river's kinetic energy directly, making them ideal for environmentally sensitive regions. Large-scale hydroelectric plants are also evolving. Replacing old turbines with modern high-efficiency designs can increase output by up to 20%. New composite materials resist corrosion and vibration, while advanced blade geometries maximize the energy captured from every drop of water. Sustainability is now at the heart of every hydro project. Engineers design fish passages, sediment management systems, and AI-powered environmental monitoring to ensure the ecosystem remains healthy. Modern simulations can predict how a river will behave decades into the future, balancing human needs with natural flow patterns. The next era of hydropower will also be defined by integration with other renewable sources. Hybrid systems combining hydro, solar, and wind power are already being built. When the sun shines, excess solar energy pumps water into upper reservoirs. When demand peaks or the wind stops blowing, the water flows back down to generate electricity. This creates a 24-hour clean energy cycle, a perfect example of harmony between technologies. In many countries, hydropower already forms the backbone of national electricity systems. Norway produces over 95% of its electricity from water, while Brazil, Canada, and Switzerland also rely heavily on hydropower for clean and stable supply. Hydroelectric plants have another major advantage: longevity. While solar panels last around 25 years and wind turbines about 30, a well-maintained hydro plant can operate for 80 years or more. Even after upgrades, the same dam can continue producing power for generations, making it one of the most cost-effective and sustainable investments in the energy sector. Water is more than just a resource. It's the planet's natural engine, a continuous cycle of movement and power connecting the sky, land, and sea. Every drop contains potential energy, and when harnessed responsibly, it becomes the foundation of a cleaner, greener civilization. Hydropower proves that technology and nature don't have to be enemies. When designed with respect and intelligence, they work together. providing renewable energy, protecting ecosystems, and driving human progress. The future of energy lies in balance. And at the center of that balance will always be water, the silent engine of our planet.